Okay. Good morning, everyone. So let's get started. So in the last lecture, we started talking about kernel methods, right? So it was motivated by generalizing our linear classifiers to nonlinear classifiers. So the trick is that I'm gonna come out with some like smart feature mapping, right? So we know that for the linear classifiers, our classification relies on a linear function over the input feature vector x, right? So W transpose x plus B. But that kind of like make a strong assumption, assuming your instances are linearly separable in your instance space, which probably is not that easy in many real-world applications. So to deal with nonlinear classifier problems, idea is that, okay, I'm gonna build up some feature map, right? I map my data instance into a higher dimensional space. This map usually is some kind of nonlinear feature mapping. We hope that in the map feature space, those data instances are distributed in the places such that we can find a good hyperplane to separate them out, right? That's the key idea. And using this idea, we can generalize our SVM to the mapped feature space. And then using the dual form, we're gonna calculate the dot product between every training example and the test example after feature mapping, right? But here comes a problem. So when we calculate the dot product or inner product between those mapped feature vectors, it brings additional computational cost, especially if you're dealing with very high dimensional mapping. Right? So here we're given one example at the end of last lecture. Right? We just consider a quadratic feature mapping. Right? Quadratic feature mapping means that, okay, suppose in the original data instance space, right, we have n features. And now in my mapped feature space, I'm gonna enumerate all the polynomial terms of order 0, 1, and 2. Right? And polynomial terms of order 0 simply is 1, right? And polynomial of order 1 are just the original features, right? X1 through Xn. But if you want to do polynomials of order 2, you're gonna combine every pairs of features, right? So it will be, you see x1 square, x2 square to xn square, and all the combination between xi and different and other features, right? x1, x2, x1, x3, x1, xn, x2, x1, x2, x3, and so on. So if we look at the total dimension after you do this quadratic feature mapping, it will be at order of n square, right? Right, because you're doing quadratic feature mapping, right? And then if we do such mapping and then calculate dot product between any pair x and z, right? The computational cost or time complexity is O(n) squared, right? We're on the same page, right? So of course, this is a kind of like make the computational costly when you have a large n. Say if your n is 1,000, right? O(n) squared means that it's 10 to 6, right? Which is 1 million. Which is already quite costly, right? If your original feature is 10,000 dimensional, and then if you do the feature mapping, the quadratic feature mapping, and then calculate the dot product, it'll be 10 to 8, right? 10 to 8 means like 100 million operations just to calculate a single dot product operation. That is really, really expensive. But this is just a very simple feature mapping. I mean, later we'll see like in many other feature maps will give like infinite dimensional feature mappings. If you're performing infinite dimensional feature mapping, that means you'll never be able to explicitly compute the feature vector. Why? Because you will never be able to compute an infinite dimensional feature vector, right? So you have to leverage some like computational trick to sidestep like explicit feature mapping and dot product. Right? So this trick is called kernel trick, but here we want to use a concrete example to show how this kernel trick is used. Right? Okay, so look at this quadratic feature mapping case, right? We have concluded that if you do explicit feature mapping, then do the dot product to calculate A, your time complexity will be O(n) squared. And here again, n is the number of features in the original data space, right? And now we propose an alternative way to compute this guy, okay? Which we denote as B, right? And B is computed as a function of the original feature vectors x and z in the original instance space. And the calculation of B never explicitly involves feature mapping. Instead, we calculate everything in the original instance space. How do we calculate? We first do the dot product between x and z. And here, there's no feature mapping. Right? We just the original feature vector, x and z, we do dot product, then we plus a constant 1 and take square. And this is our B. And if we look at the time complexity, right? Because there's no explicit feature mapping, right? And x and z are both like n-dimensional, right? So this dot product is just the time complexity O(n), right? And you plus two constant operations like plus 1, take a square, right? So doing this, we just take a linear time complexity in the number of features in the original instance space, right? It is much more efficient and cheaper to compute than this aforementioned operation, right? Then we would like to claim that the two results are equivalent to each other. And here we just relax the requirement for equivalence, meaning that we do not care too much about coefficients, because later we'll explain those difference of the coefficients will be easily adjusted. But anyway, our claim is that, okay, you can choose to compute A, you can choose to compute B. Obviously, these two computational procedures will end up with very different time complexity, but the results end up being equivalent to each other. Why is the case, right? Why they're going to be equivalent? Right? Obviously, calculating B is much more efficient, much cheaper than calculating A, right? But why the results end up being the same? We can manually check, right? We can verify this why this is true, right? So here, for simplicity, let us assume our x and z are in a plane, meaning that they are in a space of R2. So x can be represented by x1, x2. So x is represented by x1, x2, and z is z1, z2, right? So let's try to perform A, right? And then perform B, and then compare the results and verify if they are equivalent. So from the feature mapping, so this is a quadratic feature mapping over X. Okay? So just zero order polynomials, first order and second order, right? So similarly, we'll apply the feature mapping over Z, which is Z1, Z2, right? So this is pretty straightforward. I just copy and change the notation, right? So the first zeroth order, 1, first order, Z1, Z2, and second order, Z1 square, Z2 square, and Z1, Z2, right? Does it make sense? Everyone is good about this, right? At this, okay. So now let us first calculate A, right? So the calculation of A would be, just do a dot product between these two mapped feature vector. It's literally it's straightforward, right? It's 1 plus x1 z1 plus x2 z2 plus x1 square z1 square plus x2 square z2 square plus x1 x2 x2 z1 z2. Any question? Okay. Now let us look at if we calculate B, what are the results, right? So B equals 1 plus, I'm going to use a different color. So B equals, remember here's like we first compute dot product between x, z, no feature map, right? So and plus 1 and x dot product with z, which is x1 z1 plus x2 and square, right? Okay, so now let us just take square, right? This is just the practice of I don't know, grade 8 math, right? You just span the quadratic terms. We know that, okay, you're gonna first that's my way of doing this, right? Take the square of each individual term and then do the cross term, right? So the square of each individual terms will include 1 square is 1, right? x1 z1 square, which is x1 square z1 square, right? And x2 z2 square. And then all the cross term, right? So the cross term, you got this guy and this guy cross term, and don't forget to multiply 2, right? So it's 2 x1 z1 and this guy 2 x2 z2, and eventually this guy and this guy, which is 2 x1 x2 z1 z2, right? That's just the results. Now let us contrast the B to A, right? We see they're like exactly corresponding to each other, right? So if you take a look, like first order term 1, first order term 1, right? And x1 z1 2x1 z1, right? Let us forget about the coefficient right now. Let's assume, okay, if the most important thing is that we can find every term showing up in A which also showing up in B. Every term showing up in B, which always showing up in A, right? So x1 z1, x1 z1, x2 z2, x2 z2, x1 square z1 square, x1 square z1 square, right? x2 square z2 square, x2 square z2 square, right? And the last term is x1 x2 z1 z2, right? This guy, and we got 2x1 x2 z1 z2. So see that actually the results are equivalent, except a bit difference in terms of coefficient, right? But this actually doesn't matter. Why? Because this coefficients can be adjusted by just make this feature mapping by multiplying by some skew, right? If you want this factor of 2 to be reflected in A, you can just put the square root 2 here. Sorry. Here, and here, and here. Oh, sorry, here. Now you're gonna make A and B exactly the same. Any questions so far? Again, I mean, this is like a very straightforward calculation, but we encourage everyone to manually here, and to manually check this and to verify. You say these two completely different computational procedures indeed bring the same results. But what kind of insight from it, right? What kind of insight can we get, right? This example shows us, like, if we want to lift the representation in a very high dimensional space, it is possible that we don't need to explicitly compute the feature mapping, then do the dot product. It is possible that we can come out some kind of function such that by calculating this function in the original instance space, it ends up being a result which is equivalent to first do the feature mapping and then do the dot product. If you can find such a function, right, then you can dramatically reduce the computation cost of doing, feature mapping and doing linear classification in that mapped feature space. So if you can do this, right, we call you have successfully applied the so-called kernel trick. Okay, now go ahead. What is the computational cost of the one with the A has complexity of squared? Is the B one bigger or? Yeah. If you take a look at this, right? Yeah, that doesn't matter, right? That's fine. So here we assume X and Z, they are all n-dimensional, right? If you do the quadratic feature mapping, you see this guy, the dimensionality of phi X will be at the scale of n squared, right? Now, if you do a dot product between two feature vectors, which are n squared dimensional, right, the cost will be n squared, right? But if you calculate B, right, you are calculating the dot product between X and Z, not X, phi X and phi Z. And then their complexity is just O(n), right? So you see the difference in terms of complexity. But the good thing is that you can calculate B, which is much more efficiently, but give the same results or equivalent results to the calculation of A. So that's the key point, right? That means, like, if you want to, remember, if you want to extend our linear classifiers to a nonlinear case, the important strategy will be, okay, I'm gonna come out some like high complex feature mapping, and then in the high dimensional space and apply SVM dual, and then when I get those support vectors, I can do the prediction, right? The prediction requires us to calculate the dot product between every training example and test example after the feature mapping, right? That is exactly what does A do, right? What A does, right? And and unfortunately, this is very costly if your feature mapping is very high dimensional. And our concrete example shows that, okay, probably you can come up another way of doing this. You have some like a function which directly compute everything in the original data instance, but the result is the same as you lift the feature representation first and do the dot product, right? If you can find out such a function which is equivalent to doing this, right? And by calculating this function, you kind of dramatically reduce the cost. This is called a kernel trick. And this function is called a kernel function. Does it make sense? Any other question? Okay, so now let us give a kind of summary of the so-called kernel trick, right? This is actually a K of kernel method, right? So the kernel trick is such a trick that we can save the time and the space by computing the value of the kernel function, which is done by performing operations in the original space only. And then this is called kernel trick, because this kernel function is computed only in the original feature space. It doesn't do explicit feature mapping, but the result is equivalent to performing some kind of feature mapping and performing the dot product in the mapped feature space. Then this is a kernel. This is a so-called kernel trick. Okay, any question regarding definition? Okay, great. So if we use kernel trick to summarize what we have shown so far, right? In the quadratic feature mapping case, right? We want to map our feature vector, which is n-dimensional instance space, from n-dimensional instance space to a degree 2 polynomial feature space, which is O(n) square dimensional feature vectors, right? And if you don't do any kernel trick, then you doing the feature mapping and do the dot product, the time complexity will add to the scale of n squared, which is relatively expensive, especially when n is relatively big, right? Like 1,000 or 10,000, it will be very, very costly. However, if we apply the kernel trick, that is, we compute a function of x and z by doing the operations only in the original feature space, which is just in the Rn, right? And then the time complexity dramatically reduces to On, which is just linear in the dimensionality of the original instance space, right? So that's a big saving of the computational cost and also storage, right? You never need to explicit store the mapped feature vector, right? This is also big storage space. Okay, so now we have give a kind of formal definition about kernels and kernel trick. Let us look at the properties of kernels, right? So a straightforward intuitive question would be, okay, can we use an arbitrary function, right? Arbitrary function means that arbitrary function which has two input feature vectors, right, and give you some kind of value to perform kernel trick. Right. Can we like composite any functions of two input vectors to perform kernel trick? Can we? Just give me a guess. Any guess? You think yes? Okay. Yeah, unfortunately, the word is not ideal. Yeah, kernel trick is very good, right? It helps you like reduce a lot of computation costs. You don't even need to worry about how the feature mapping is conducted, right? But that doesn't mean like for every bi-variable input as functions, you can use it as a kernel function to perform kernel trick. I mean, this is kind of like consistent with the real world, right? There's like, I mean, for good things, if something is good, like it cannot be anything, it cannot be everything, right? There are also some kind of like speciality on those good things, right? So unfortunately, we cannot claim that an arbitrary bi-input function would give us this kernel trick benefit. Instead, in other words, we can only claim if a bivariate function k is valid kernel if it indeed corresponds to an inner product in some feature space. That means if I just pick up a function, right, that has bivariates as inputs, right, x and z, right? If you say it's a valid kernel, you need to ensure there exists some kind of feature mapping. Although you probably don't know that, you don't see that, but you should make sure that it indeed corresponds to some kind of feature mapping over x and over z, and then do the dot product. Otherwise, it's not a valid kernel, meaning that for you random pick up a function x about x and z, they might not correspond to any feature mapping and their dot product. Okay. Then a natural question will be, suppose I give you some kind of function k, right? And can you justify it is a valid kernel function or not? And most straightforward way of doing this is that, okay, you are gonna accord according to the k, and you want to come out some feature mapping, you want to show the equivalence, right? This is not easy, right? This is definitely not easy, right? So we're not gonna verify this through the definition. Instead, we're gonna give some other conditions to claim the function k is a valid kernel. Right? So this is a general condition. The basic idea is that I'm gonna construct a Gram matrix over an arbitrary set of inputs like x1, x2 to xn, right? And if you can show that no matter how you pick up a set of inputs, and no matter how large the set of inputs, you use your function k to construct a Gram matrix. And if this Gram matrix is always positive semi-definite, then this function k must be a valid kernel, and it must correspond to some feature mapping, perhaps is highly complicated, and your kernel function k is equivalent to performing feature mapping and do the dot product. Right? So that's the idea, right? So now let us explain what does mean for like Gram matrix and so on. Right? Okay. So first, we would like to review the concept of positive semi-definite. Right? So we call a symmetric matrix M is positive semi-definite if for any non-zero vector z, we have this quadratic form z transpose mz non-negative. Right, this is the definition of the positive semi-definite. And I believe everyone has seen this in your linear algebra course, right? And if we could recall more, we know that for the positive semi-definite matrices, all their eigenvalues must be non-negative, right? That's the basic properties of positive semi-definite matrix. This concept is very, very important. It's not only used for here, right? It's actually used in many mathematical theorems or assumptions or conditions and conclusions and so on. Okay, any question regarding the definition of positive semi-definite? Okay. Now let us look at what's the definition of the Gram matrix. So when we say we want to construct Gram matrix, the construction is done on a set of input vectors, which we denote by x1 to xn. So we have a set of n vectors S, right? Then from S, the Gram matrix will be constructed as an n by n matrix G, where each element in G is the dot product between two vectors, like GIG, like, you know, column I, row I, column J is defined as the dot product between X and XG. Right? So we can imagine that if we do some kind of feature mapping, right? So X1 to Xn after feature mapping in some high dimensional space, you still have like n vectors, right? Which is phi x1, phi x2 to phi xn, right? You can still construct grand matrix on those mapped feature vector, right? And then in that case, right, Gij will be just dot product between phi xi and phi xj, right? So now let us consider this grand matrix G. Our claim is that the grand matrix is always positive semi-definite. Why is that the case? This is actually a practice, a linear algebra course, right? We just quickly show that. I mean, again, if you feel uncomfortable, that's totally fine. That's a good thing. After you review this lecture, you just quickly review what we have learned for our linear algebra before, right? So if we look at G, right, we know that this is x1 transpose x1, x1 transpose x2, blah, 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 x1 transpose xn, right? Every element is just dot product between, one vector and another vector, right? So if you just write it down, it will be xn transpose x1, xn transpose x2, da, 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 xn transpose xn, right? Now, if we view this G as some kind of this particular matrix, which is denoted by X, is just stacking all these n vectors. Namely, each row is just one vector, x1 transpose to xn transpose, right? It's pretty straightforward to see that G equals to x transpose, right? You can verify it by yourself, right? But it's just straightforward to verify, right? And this structure actually ensures G is always positive semi-definite. Why? Let us check. Let's check, right? So suppose you got some non-zero vector, which is d-dimensional, right? According to the definition, if G is positive semi-definite, then this arbitrary Z, non-zero Z, will give you Z transpose G, Z always non-negative, right? That's the definition. So we can take a look, right? Because G is structured with like X, this big X matrix, X transpose with small z. What can we observe? What is positive semi-definite? Yeah, the definition is here, right? It's positive semi-definite if for any vector of non-zero, we have Z transpose MZ, non-negative, right? That's the definition. Now here we just verify the definition, right? So we verify G is positive semi-definite, so we pick up an arbitrary non-zero vector Z. We want to look at whether Z transpose GZ is non-negative, right? So because we found out G has this structure, right? G is this X matrix multiplied with the dot product, the transpose of X matrix, right? So if we substitute for G, we have this projected term to be Z transpose X, X transpose Z, right? So now, can anybody tell me, is this number non-negative or not? Exactly, right? So if you look at this guy, right? This is a vector, right? So if you look at this guy, this is some vector, so we denote as H, right? So this whole quadratic term essentially is H transpose H, right? Right. So you see that dot product between a vector and itself is always non-negative, right? So that means like this guy is non-negative. G must be positive semi-definite. Any question? Okay. So Gram matrix is showing to be a positive semi-definite, right? So now let us consider things, right? One thing. If your given function k, say this bivariate function k, right? It really corresponds to some feature mapping. That means there must be some feature mapping phi such that you apply phi over x, you apply phi over z, and then do the dot product, it will be the same as kxz, right? So that means like if in a Gram matrix G, you replace each term by the kernel function between the corresponding vectors. And if this kernel is valid, right? That means this kernel function corresponds to phi xi transpose phi xj. Then G must be a positive semi-definite as well, right? Does it make sense? Like, so remember, our goal is that, okay, I want to look at for arbitrary given bivariate function kxz, if it is a valid kernel. What does it mean for being a valid kernel? It means that, okay, this k corresponds to some feature mapping phi, right? So if it really corresponds to a feature mapping phi, then if you use k to construct this Gram matrix, namely, you're going to replace every element of G to be a kernel function between xi and xj. Then this element should be, you perform the feature mapping over xi and feature mapping over xj and do the dot product, right? Then the G should be a positive semi-definite. So following this intuition, there is some kind of theorem telling that if for every finite set of like input vectors, if you use kernel k to construct the Gram matrix, and if this Gram matrix is always positive semi-definite, then we'll conclude your proposed kernel k is a valid kernel. This is called a Mercer kernel theorem. Let me repeat this again, right? So let k xz be a function that maps two n-dimensional input vectors to a real number. So we can come out arbitrary like a bivariate function k, right? And which give you two input vectors, you map it to a number, right? I want to look at if this k is a valid kernel, right? How can I verify, right? The idea is that, okay, I'm gonna enumerate every possible finite set of input vectors x1 to xn, whatever, right? N can be arbitrary large or arbitrary small, right? And if I use k to construct Gram matrix on this set of vectors, and this Gram matrix is always positive semi-definite, then we claim k is indeed a valid kernel, right? And this is just another way to write up like the kernel, the Gram matrix you construct by k is positive semi-definite, right? This is actually like C transpose K C. It's non-negative. So this is called the Mercer's condition, a Mercer kernel theory. And intuitively, as we just explained, right? If K indeed is a valid kernel, then the Gram matrix you constructed, each element should be the dot product between the corresponding feature map, right? And it should be positive semi-definite. Right? This theorem just gives you a rigorous description. To make sure that your K is indeed a valid kernel, you have to make sure, like, for every possible finite set of input vectors, the matrix you construct by K is always positive semi-definite. Then we eventually conclude your K is a valid kernel. It indeed corresponds to some feature mapping. Any question? Okay. So now let us look at set of commonly used kernels. Right. The first one is called linear kernel. Linear kernel is just a dot product between X and Z. So basically, you are not performing any feature mapping. Right. And we also do like polynomial kernel. But here we can specify the degree. So X transpose Z take the power of D. Right. And remember the example we are showing that D is just 2, right? And if we want to further enrich our polynomial feature mapping by including not order of degree D polynomials, but also all the lower degree polynomials, right? We can add a constant C to X transpose Z and then take the power of D, right? And in our case, in the concrete case, we have discussed C actually equals to 1 and D actually equals to 2, right? And actually includes all the polynomials of degree 0, 1, 2. But you can increase D. That means like you can include even more higher order polynomials, the 1, 2, 3 until D. Right? It includes all interactions of order D or lower. Okay, so here is another very, very popular kernel function, which is called Gaussian kernel. So what is Gaussian kernel? Given two input vector X, Z, we're going to first compute the square of the Euclidean distance between X and Z and divide it by some constant C, which is just the free parameters, but must be positive, right? And then you take exponential to the negative of this guy. This is called Gaussian kernel. Why is it called a Gaussian kernel? Because it looks like a Gaussian density function. Right? And here we want to conclude that the feature mapping correspond to a Gaussian kernel is infinite dimension. So in other words, you will never be able to explicitly compute the full feature vector, map the feature vector corresponding to Gaussian kernel. And here we're going to leave two exercises for you. Right? First, can you prove Gaussian kernel is a valid kernel using Merther condition or Mercer's theorem? As we just mentioned, right? If you use this Gaussian kernel to construct Grand matrix over an arbitrary set of input vectors, the Grand matrix is always positive semi-definite. Right? This is one thing. Second thing, can you figure out what is particular infinite dimensional feature representation or mapping implied by the Gaussian kernel? That will probably show up as a bonus question of our next homework, right? But you can start thinking about that. But actually, Gaussian kernel is just one case showing that, okay, your feature mapping could be infinite dimensional. And there are a lot of like popular kernels which also have like infinite dimensional feature mapping, like Mertern kernel, Mertern family. They're all infinite dimensional. So for this infinite dimensional feature mapping, we indeed cannot explicitly compute the dot product after feature mapping, right? We have to leverage this kernel trick. Okay, sometimes like people want to construct new kernels. If we don't want to construct new kernel from scratch, right? Can we combine existing kernels in a very simple way to construct more complex kernels? Right? The answer is yes. And we can follow several basic rules of doing this, right? For example, if you multiply some existing valid kernel function by a positive constant c, then it's still a valid kernel. And if you have an arbitrary function f, which applies to the original input in the original input space, then fx times k times fx prime also forms a valid kernel function. Okay. And you can also throw a kernel function into a polynomial of like arbitrary degree, and this composite function is still a valid kernel function. Okay. Or take exponential, also a valid kernel function. Okay. When you add the two kernel functions together, it ends up being another valid kernel function. We'll multiply them together, you end up with another valid kernel function. So through those basic rules, right, you can construct a variety of complicated kernels out of existing kernels. Okay. Any questions so far? Everyone's good? Okay, great. So the last thing about SVM is how do we combine the kernel tree and SVM dual to really empower our SVM to do a nonlinear classification. Okay, so we need to go back to look at the SVM dual form, right? If we can recall, right, we first construct primal form of SVM, and then switch max min, and then do the inner minimization and simplified form, and end up being our SVM dual problem being like this, right? You're going to minimize this quadratic function regarding the Lagrange multipliers, alpha i's, right? And subject to this constraint, like h alpha I is between 0 and c, and the summation of r alpha I y's are 0. And you minimize this guy, we can use arbitrary any like convex optimization package to perform this quadratic convex optimization. Okay? So then the key observations here is that in this dual form, we need to compute the dot product between every pair of the training instances. Okay? So now consider we extend our SVM by mapping the feature vector in the original space to some higher dimensional feature space through some mapping phi, right? Then in this mapped feature space, our SVM dual should be written as phi xi transpose phi xj, right? Does it make sense? Right. And why do we perform feature mapping? Why do we perform feature mapping? Yes, exactly, right? Remember, all those things we have discussed so far, right? We want to enhance the capability of SVM. We want like not only doing linear classification, also want to do a nonlinear classification, right? That's why we want to come out some like complicated feature mapping to some new space. In that space, we do some linear, we learn some linear classifiers, right? So in this mapped feature space, in this new feature space, of course, the dot product becomes will be performed on those mapped feature vectors. That end up being like phi xi transpose phi xj. Does it make sense? Okay, and then through the kernel trick, we can see that we actually do not need to explicitly compute the feature mapping and do the dot product, right? We can just replace this dot product by a kernel function, a valid kernel function between of xi xj, right? Then this corresponds to our objective function, a learning objective for nonlinear SVM classifier. Any question? And the good thing is that because we're optimizing about R of i's, right? So this dot product or the kernel function actually is some coefficient in front of terms, including alpha I, alpha j's, right? It doesn't change the optimization nature. The optimization is still a quadratic convex optimization problem. You can apply exactly the same optimization package algorithm to do the things. The only change is how you're gonna compute the dot product. We're gonna replace the dot product by a kernel function between x and xg, and that's it. So that's why it's so convenient. And then after we have solved this nonlinear SVM objective function, right? We got optimal alpha i's, right? And when we make a prediction, remember, when we make a prediction, we need to compute the dot product between the optimal weight vector and the mapped feature vector over the test input x, right? This again requires us to compute the dot product between the mapped training instance and mapped test input, right? And this again can be replaced by a kernel function. So you see that for both training and prediction, you just replace the dot product by the kernel function. Nothing changed in other places. Then you have finished the training and the prediction of nonlinear SVM. Any questions so far? Is everyone comfortable? Any question? So you can see that we end up with very succinct form, right? Very succinct form, very simple replacement, and just replace the dot product by the kernel trick, right? But to arrive this, we have to go through a series of like, simplification, calculation, derivation, all kind of stuff, right? But the results are really beautiful, really elegant. It's very simple. We just replace xi transpose xj by a kernel function between xi and xj. That means we're going to extend our linear SVM to nonlinear SVM, and that's it. And so same thing applies to the prediction step, right? In the prediction step, if you're doing linear classifier, then it should be xi transpose with x, right? But now we just replace it by k xix, then we're doing nonlinear prediction. And then we'll finish our extension of SVM to perform like very complicated cases. Okay. And someone might ask, right? In this case, how do we recover B? Right? And if we could recall, right, the optimal weight vector is pretty easy to get. That is, you just do a linear combination of those feature vector, combine and multiply with the optimal Lagrange multipliers of i's, right? But how to get B? We mentioned that you have to pick up some optimal Lagrange multiplier alpha j, which is strictly between 0 and c. And then through some kind of inference, we know from slack, complementary slackness, and also the results of the intermediate optimization step, we can derive that optimum B would be the label yj subtracted by the dot product between the optimal weight vector w and xj. Right? So same process applies to the map feature space. Because in this case, right, if we want to compute W star dot product with the mapped feature vector, which again requires us to compute the dot product between every instance and the test input x after feature mapping. And again, this guy can be replaced by a kernel function. So basically, we just replace this dot product between the weight vector and x by our new representation in terms of kernel function and the optimal Lagrange multipliers alpha i's, we get our optimal B. And then once we get B, we can perform prediction for arbitrary new test examples. Right? Any questions so far? Okay, so we want to emphasize that the final form of the SVM, nonlinear SVM, is quite simple, quite concise. But we expect everyone that could follow the whole inference on derivation procedure. How do we arrive at this final objective function? Right? How is kernel trick is obtained, motivated, and how the nonlinear SVM dual is formulated, simplified, and get this form, right? And how are they combined together? The combination is straightforward, actually. Okay, so here we want to give some concrete example about nonlinear SVM. Suppose we perform a nonlinear SVM with this Gaussian kernel. Remember, the Gaussian kernel corresponds to some like infinite dimensional feature space, right? You can only imagine, right? After you map those data points into an infinite dimensional feature space, in that space you got some hyperplane which will separate out positive examples, negative examples. But if you map your hyperplane in that infinite dimensional feature space back to the original feature space, then your margin, the linear classifier, the classifier boundary will be nonlinear, right? Because your feature mapping, right? Your x to phi x is nonlinear, right? When you from the nonlinear feature space mapped back, of course, it will be nonlinear as well. And this figure just to showcase like what does those classification boundary look like in the original instance space. Right? So there's positive examples, negative examples. Obviously, in the original space, those blue dots and the red dots, positive, negative examples are not linearly separable, right? So you can imagine through this Gaussian kernel, they're essentially mapping those dots to infinite dimensional feature vectors, and in that infinite dimensional space, you got a nice hyperplane separate them out, right? And you have some like margin, right? And the classification boundary, right? And when you map those margin and classification boundary back, you see they correspond to some like curve like this. Those level set like this curve like this. And those circled points represent the support vectors. Okay, any questions so far? Hopefully this example will give us like a more concrete feeling about non-SVM. Okay, now we have finished up. We haven't finished the discussion about SVM and the kernel method, right? So here is a summary. Right? When we talk about support vectors, the support vectors come from the dual form of SVM. And through the dual form, we know that the optimal weight vector actually is only determined by a linear combination of a subset of training examples, right? If we could remember, right, the optimal weight vector essentially is just a set of alpha g star xg, right? And those xg with non-zero alpha j's are called support vectors. And if you use this dual form to solve SVM and to get the SVM solution, then we reconstruct W and make prediction. You see that the prediction essentially requires the computation of the dot products, between the training example and the test example, right? And the kernel trick is a computational trick. Help us to reduce the complexity of the dot product. Because if we perform the feature mapping in a higher dimensional feature space, if we're explicitly performing the feature mapping in the dot product, that will be expensive. And even infeasible if your feature map is infinite dimensional, right? So the kernel trick can avoid this, can sidestep this issue by just computing everything in the original feature space. So it's much, much cheaper, right? So kernel trick is then applied to SVM to perform implicit feature mapping and nonlinear classification. But kernel trick is by no means just applied to SVM. Actually, it's a very widely used trick. It's a general trick applies to linear methods, the linear models. For example, you can apply the kernel trick to perception. And this version of perception is called kernel perception. And again, we leave it as an access for everyone to think about how do we extend perception to nonlinear perception. Okay. Any questions so far? Okay. So now, mhm.
How is this different from, for example, modeling the population, the level 0 and 1, just with the kernel function, we model the probability density function, and we use that to justify it.
Well, this doesn't assume any probability density function. It doesn't make any assumption about, okay, how the label.
The function over each training point and sum them up, I would then end up with some non-parametric dimension of the probability function. So the assumptions are.
Well, yeah, I think talking about like kernel density estimator. Well, this is a completely different story. Well, well, it's out of scope of our class, but I can give you some kind of idea. Like the kernel density estimator is trying to use kernel function to estimate the probability density of the data points, right? Actually, it's not the same as we want to calculate the dot product between the data points, but they're kind of like share the idea in that like it is still based on similarity, right? If we look at if the kernel density estimator means that okay, I want to generalize the empirical distribution. So the empirical distribution means that okay, I have a bunch of data points, right? And for each data point, I have a point mass. I use this point mass to construct mixture distribution to approximate the original distribution. This is kind of good, but this is a discrete distribution. It's not continuous distribution. Kernel method, the kernel density estimator is try to continue doing some continuous version of density estimation. But if you're doing continuous version, you have to consider this, like the similarity at any position from all the examples you have seen so far. That's why they use kernel function. Another question? Okay, so I think the last 10 minutes, we would like to introduce the cross validation. Right? That's a very commonly used trick for hyperparameter selection and determination in machine learning practice, which is I think is very useful for everybody to know, right? So, so what is cross validation? Suppose we want to train a classifier using some given data set, right? Given some hyperparameters. Sorry. It's here, right? So how do we know which hyperparameter is the best? Okay. And we can use SVM as an example, right? And let us consider, for simplicity, let us just consider the primal form of SVM, which is just you know, the loss is the square norm of W plus C plus the hinge loss, right? Hinge loss is max 0, y minus y n w transpose xn plus b, right? Something like this, right? And the hyperparameter c, which is bigger than 0, indicates the trade-off between the margin and the data fitting, right? So the problem is that how do we determine c? Should we set c to be 1, to be 10, to be 0.1, and so on? Right? So the first idea to determine the c might be that I'm just jointly minimize this loss function with respect to W, B, and C, right? So now I want to ask, what's the problem of doing this? Is there any problem? Like, I want to find out what is optimal C. Can we just optimize the loss function directly along optimize C and B, W and B altogether by minimizing L, the loss function? Can we do that? Yeah, so someone like disagree, right? Okay. Any thought about on this or any guess on this? Nope. Why? Memorizing the training data. Maybe it's not that severe. We can think about that, right? If we're really doing this, what's the consequence? What optimal value C? What optimal value of C will we get? 0, right? Right? If the goal is just to minimize this loss function, right? We know C must be non-negative, right? If we want to minimize this, of course, I'm going to set C to be 0. And if we set C to be 0, what happens? You're not training, right? And remember, this guy represents the data fitting is a hinge loss, right? If you set your data loss, like hinge loss is 0, that means you're not really training your model to fit data, right? So basically, if you just optimize hyperparameter C along with model parameters, it end up with training failure. So we cannot directly optimize hyperparameters by minimizing the loss. We have to seek out, we have to resort to other strategies. One common user strategy is called k-fold cross-validation. So what is k-fold cross-validation? Right. We can consider like we're gonna split data into k parts, right? And k is usually taken as 5 or 10, right? Sometimes you can take k to be 3 if you don't have if you don't have enough examples, right? So we partition this data into like 5 parts, right? 5 subsets, right? Every time I'm gonna use 4 subsets for training, and then train our model and make prediction on the 5th subset. You can imagine this 5th subset is like a surrogate of like general test data, right? And you can use that proxy of the general test data to evaluate the generalization performance under the current choice of hyperparameter C, right? But just doing this once might not be stable. I'm gonna repeat it doing this, right? And the next time I'm gonna use the 4th subset as the test set, and train our model on the other 4 subsets, and I get a second accuracy as an estimate of the generalization performance. Right? I just keep doing this, right? I enumerate every subset as my test set, and use the remaining part as the training set. And remember, every time the training and test sets won't overlap, right? And those are small set of training data set can give some kind of rough estimate of generalization error, and repeat through k times, and k here is 5, and average all my test accuracy as a more reliable estimate of the generalization performance of our model under the current choice of hyperparameter. Okay? So I use this cross-validation accuracy. The average of those guys are called the cross-validation accuracy. And I use this cross-validation accuracy as a performance metric for the current choice of hyperparameter. Okay. Now I can look at a different hyperparameter, and then I perform this cross-validation again to get another cross-validation accuracy. Right? I just loop over all possible candidates of my hyperparameter choice C, and then pick up the one who has the largest cross-validation accuracy. And in this way, I find out my optimal hyperparameter value. This is called cross-validation. Any question? Everyone's good?
Which
it's flexible. So, but the most often used practice is k equals to 5 or 10. Right? And also say k equals to 3. Any other question? Okay, then we can summarize the k-fold cross-validation strategy. I just want to give a more formal summary of this procedure, right? So first, we're gonna split the data into k equal sized parts, right? K is often chosen to be 5 and 10, but again, this is like application dependent. You can freely choose k, right? And then I train a classifier on k minus 1 parts and evaluate on the remaining one. You repeat this procedure using each of the k parts as the validation set. And after doing this, we can get a quality measurement for this particular hyperparameter choice by averaging the k estimates of the test accuracy, right? You got the metric performance measurement for one choice hyperparameter, but you're gonna have like maybe 10 possible choices. You run cross-validation for each choice. You got a performance metric for every choice. You pick up the one who has the largest cross-validation accuracy. Repeat for every hyperparameter choice. Right? So usually in practice, right, you probably have multiple hyperparameters. That basically means that, say, you gotta have a C1, C2, C3, right? You have 3 hyperparameters. Each hyperparameters, you might have a range of choices, maybe 0.1, 0.2, 1, 2, 10, right? And this guy might be minus 0.5, 0, 0.5. This guy might be minus 1, 2, 3, 100, right? So you're gonna enumerate all possible combinations of those hyperparameter choices. And for each combination, you run this cross-validation to determine what is the generalization performance metric for that, right? And then once you run the cross-validation over all combinations, you pick up the particular combination which gives you the best cross-validation accuracy. You use that as your final choice of hyperparameters. That's the typical procedure. Of course, this sounds very, very expensive, right? But yeah, that's the how. If you want to do practical machine learning, this typical procedure you're gonna do. Any question? Okay. Okay, then we finish the introduction of cross-validation. And we will, in our coming homework, like homework 4, which will be released on next Tuesday, we'll see like you're asked to implement SVM classifier, and the linear one, the primal training, and dual form, and nonlinear SVM, and also we request you to use cross-validation to determine what is the best hyperparameter C. Okay, see you on next Tuesday.